All right, so this is section 3.7, and this section is a bit longer, so we're going to split it up into two parts. The first part, we're going to learn all the information that we need to graph rational functions. And then in part two, we will actually practice graphing some rational functions. So a rational function is just a function that is a polynomial over another polynomial. And as always, we cannot divide by zero. So the values that make our denominator zero will be undefined. We'll see what happens at those values. But to start off, we're just going to practice writing the domain of rational functions. And again, we can't ever divide by zero. So any of those values that make our denominator zero, we cannot include in the domain. So in these first couple examples here, we can see that we have some values here in the denominator that make the bottom zero. X equals 0, x equals 2, and x equals -5 are all values that would make our denominator 0, so x is not allowed to equal those values. But that does not state our domain. We always want to state the domain in interval notation. We've been using interval notation throughout this class so far, and so we want to continue doing that. This just says what x is not allowed to equal. If I want to say what x is allowed to equal, it's really helpful to put these values on a number line. And we have -5, 0, and 2. And we know that x cannot equal these values. So I'm going to put an open dot on each of those. But there's no other restrictions. X is allowed to be anything except for these values. So when we see these numbers on a number line, we can easily see here that it's going to take 4 intervals to list all the values x is allowed to equal. So my domain here is -infinity all the way to -5. And we're using a parenthesis because it cannot equal -5. And then we have from -5 all the way to 0. And then again, parentheses on 0 because it cannot equal 0. And then 0 to 2. And then 2 to infinity. So that is the domain for this function. Now, in the next example, it's not factored for us. That first example, we already had the denominator, and so we need to go ahead and factor it. So if I factor that denominator, I have f of x is equal to x over x plus 3x minus 3. And so we have x plus 3 and x minus 3. X cannot equal 3 or -3 then. And we can do the same thing that we did in the previous example. We have -3 and 3. We can put open dots on both of those. And then x can be anything else. So we can go ahead and state our domain then in interval notation, -infinity to -3. Negative, you know what? I missed my union symbol there. There we go. The union, and then -3 to 3, and then 3 to infinity. Let me slide that over there. All right, so that's the domain for that function. Looking at the next one, it's also not factored in the denominator, and it's not factorable in real numbers. If I was to figure out what makes this denominator equal 0, I would have to use imaginary numbers. Let's try, for example, to find some numbers that might make the denominator 0. If I chose +3 squared is 9, 9 plus 9 is 18. That's not 0. -3 squared is 9, 9 plus 9 is 18, and that's also not 0, so that's not it. Maybe 1/3. 1/3 squared is 1/9. 1/9 plus 9 is 9 and 1/9, and that's not 0. I could plug in 0, and that's 0 plus 9, and that's 9. That's still not 0. So there's nothing I could keep trying numbers, but there's no real number that I can plug in for x that will make my denominator 0. So there's nothing to factor here. There's nothing that can make my denominator 0. So my domain is -infinity to +infinity. There's no restrictions on it. All right, So in this next kind of part here, we are going to explore what our most basic rational function looks like by plugging in some values. Here I have, actually, let me go above it real quick, excluded values. These values here that I was saying x was not allowed to equal, those are called excluded values. They're excluded from the domain. All right, so this next part here, we have our most basic rational function, 1 over x. And if I were to plug in negative 100, I would have 1 over negative 100, which would be 0.001. Okay. And then if I plug in 1 over negative 10, and then that would be 0.1. Oops, I had one too many zeros here. And then if I plug in negative 2, 1 over negative 2 is negative 0.5. Plugging in negative 1, 1 over negative 1 is negative 1. And plugging in 0.5, 1 over negative 0.5 is negative 2. And plugging in 0.1, 1 over negative 0.1 would give me 10. And plugging in 0.1 over negative 0.01, that would give me negative 100. And I can keep plugging in smaller and smaller and smaller values, but I can't plug in 0 because 1 divided by 0 is undefined. I can't ever divide by 0. So we're just going to write undefined there. And then similarly, you'll see those same values on the right-hand side here, just positive. So plugging in 0.01 would give us 100. Plugging in 0.1 would give us 10. Plugging in 0.5 would give us 2. Plugging in 1 gives us 1, 1/2, 1 over 10, and 1 over 100, or 0.5, 0.1, 0.01. And so we can see what happens as our numbers get really, really small, and we can see what happens as our numbers get really, really big. So what we're going to do now is plot those points that we just did a table for. And I'm not going to do all of them. I'm not going to plug in all the way to 100, but I am going to do all the way to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So we're going to plug in those values and draw our graph. So if I plug in not negative 100, but let's say negative 10, and we got 0.1. We got that really, really tiny, tiny decimal just above the x-axis. And then if I plugged in negative 2, that gave me 0.5. Again, small decimal, but a little further from the x-axis. And then plugging in negative 1 gave me negative. Ooh, you know what? I am plotting these all as positive values. These should all be below the x-axis. And negative 1. Okay, there we go. And then plugging in negative 0.5 gave us negative 2. And then plugging in negative 0.1, really, really close to 0, but not quite touching 0. So just slightly to the left of 0, all the way down to negative 10. Again, really close to the y-axis, but not actually touching it. And we can see what's happening here. Our graph is getting this really tight curve in here and then shoots way down to negative infinity and gets really, really close to 0, but never actually touches it there. And then the same kind of thing is happening on this side. So plugging in, I won't do 0.01, but plugging in 0.1 gave us 10. Plugging in 1/2 gave us 2. Plugging in 1 gave us 1. Plugging in 2 gave us 1/2. And plugging in 10 gave us 0.0 or 0.1. And there is our curve on that side. And I got a little close here with my pen, but we can see here that it's getting really, really close to the x-axis, really, really close to the y-axis, but never actually touching either one of them. And what we have here is a vertical asymptote and a horizontal asymptote. Okay. When I do these in my notes, I either use like a yellow pen or a highlighter just to distinguish them. Um, I do want to always see your asymptotes graphed. So make sure that on like a test, you always make sure to graph those. And so we have these asymptotes here, and the equation of the horizontal asymptote is the line y equals 0. And the equation of the vertical asymptote is x equals 0. And vertical lines are always of the form x equals a number because at this value, x is always 0. And here at y equals 0, this is a horizontal line, y equals 0, because at this line, y is always equal to 0. So those are the equations of our asymptotes here. Again, this is a horizontal asymptote. I'll usually abbreviate it as HA and VA for our vertical asymptote. So this is the graph of our most basic rational function. On the next page, we are going to graph another basic rational function using points. We'll use a few less points than we did on this one, but that's the kind of parent rational function. All right. I'm actually going to skip over this arrow notation until we do this next graph, and then I'll come back to that. But we're going to go ahead and graph the equation 1 over x squared this time. I'm going to go ahead and make a table of points off to the side here, and I'll go ahead and plug in a few points. I'm going to plug in, let's say, -3, -2, -1, -0.5, 0.5, 1, 2, and 3. Okay, plugging in -3 squared is 9, so that's 1/9. Plugging in -2 squared is 4, so 1/4. Plugging in -1 squared is 1. 1 divided by 1 is 1. -0.5, well, -0.5 squared, that's actually going to give us 1/4. 1 divided by 1/4 is 4. We can't plug in 0, that's undefined, just like with the last one. Plugging in 0.5, we also get 4. 1/2 squared is 1/4. 1 divided by 1/4 is 4. Plugging in 1 squared is 1. 1 divided by 1 is still 1. Plugging in 2 squared is 4. 1/4. And 1/9. So you'll notice with this one, none of the values were negative. They were all positive values. And that's kind of one of the differences when that denominator is squared, because any negative value, when it's squared, becomes positive. And so we're going to plug in these values here. And when I plug in -3, we got 1/9. Let me use a different color here. So really small decimal, almost to the x-axis. 1/4, 1, and then plugging in -1/2, -1/2, we got 4. And then we can't plug in 0. And then plugging in +1/2, we also got 4, 1, 1/4, 1/9. So we can see the shape of our graph. And that's what that graph looks like. So we still have a vertical and horizontal asymptote, as we can plug in x values closer and closer to 0, but we can't plug in 0. And as our x values get really, really big and really, really small, our function goes to 0. It gets really close to the x-axis, but never actually touches it. So again, the equations of those lines are y equals 0 and x equals 0. So that arrow notation that we have up above, let me see if I can zoom out a bit here. And so we have this arrow notation that you will see a lot in calculus, especially at the beginning of calculus when you are looking at limits. And so you want to get a little bit familiar with this notation. So we can talk about what's happening as a is getting really, or as x is getting really close to some value. And on your notes, you might see this little minus sign. It's kind of hard to see on the screen here, but there's a little minus sign there up on the a. And what that means is we're getting really, really close to some value from the left-hand side. On the next one, we see a little plus sign. And that means we're getting really, really close to a as from the right-hand side. We can talk about x getting really big, x going to infinity, f of x going to, or x going to negative infinity, f of x going to infinity, and f of x going to negative infinity and approaching a value. But these make a lot more sense when we're talking about an actual graph. So let's look at the one that we just did. So if I'm writing the arrow notation there, I can talk about as x gets really, really, really big, as x goes to infinity. So as x goes to infinity, my function f of x is getting closer and closer and closer to 0. So it's a way of describing what's happening in our graph. I can say as x is approaching 0 from the right-hand side, so as x goes to 0 from the right, f of x goes way up to infinity. And as x goes to negative infinity, f of x goes to infinity. Okay. So that's that arrow notation. Oh, you know what? I didn't say as x goes to 0 from the left-hand side. So as x gets closer and closer to 0 from the left-hand side, f of x goes up to infinity. I actually combined those two. This one should not say infinity. As x gets closer and closer to negative infinity, my function is getting closer and closer to 0. All right, so that's that arrow notation. The next thing we're going to take a look at is vertical asymptotes. And kind of the short answer to how to find a vertical asymptote is it's what makes the denominator 0. Except if they cancel. So if you have a factor up top and on bottom that cancel out, then that gives you what's called a whole. If you have a factor in the bottom that makes an asymptote, so this being an asymptote here, that gives you a vertical asymptote. So let me tell you what a whole is really quickly. If you have a graph here, and let's say we have some curve, and we have a literal hole in the curve there where there's one single x value where it's undefined. Let's say this is x equals 2. Okay. Well, what that means is that I have a factor of x minus or x plus x minus 2 over x minus 2 that canceled out, and that's what created the hole. If I have a factor in the bottom that didn't cancel out, let's just say x, and that's x equals 0, then we would have a vertical asymptote at that value. So that's what we're going to look at in these next couple examples. Let me zoom back in on the problems a bit here. So it says find all the vertical asymptotes, if any. We're also going to state if there's something that's a whole. So the first thing I need to do is factor top and bottom of each of these. So on top here, I just have x. On bottom, I have x plus 1, x minus 1. Over here, I have x minus 1 on top, and on bottom, I have x plus 1, x minus 1. And for this one, there's no way to factor that denominator. It's just x minus 1 over x squared plus 1. So for this first one, there's no factors that cancel between the top and bottom. So both of these factors on bottom, that would give my denominator a 0. Those both give me a vertical asymptote. So my vertical asymptotes are x equals negative 1 and x equals 1. For the next one, I see that I have a factor that cancels out. This factor of x minus 1 and x minus 1 cancels, and so that gives me a whole. So I have a whole at x equals 1. And then this factor here, x plus 1, gives me a vertical asymptote at x equals -1. And you might be wondering why those signs are switching. What we're saying is what would make this equal 0? X plus 1 equaling 0, -1, -1, x equals -1. So what we're saying is that factor, what would make it equal 0? All right, and then the bottom one, like we saw before with the x squared plus 9, there's nothing here that I can plug in for x that would make my denominator 0. There's no way to factor this in real numbers. We would have to use imaginary numbers. And so I could try plugging in -1. -1 squared is 1. 1 plus 1 is 2, so that's not 0. I could try plugging in 0. 0 squared is 0, plus 1 is 1. That's not 0. So there's nothing that makes my denominator equal 0, which means I have no vertical asymptotes. All right, on to the next page, talking about horizontal asymptotes. And horizontal asymptotes are a bit more involved than vertical asymptotes. Horizontal asymptotes, there's 3 different scenarios we have to kind of be aware of. So if you have a rational function and you are trying to find your horizontal asymptotes, we want to look at the degree of the top and bottom. So if this is the top function and this is the bottom function, this n value and m value are the degree of the top and bottom, then again, that's the largest exponent up top, largest exponent in the bottom. If the degree of the top is smaller than the bottom, so sometimes I'll kind of write off into the side here, top smaller, then the equation y equals 0, which is the x-axis, is your horizontal asymptote. If the degree of the top and bottom are equal, so same, then you have the equation of their leading coefficients, an over bm. These leading coefficients of those 2 terms is the horizontal asymptote. And then if the top is bigger, then there's no horizontal asymptote. Okay. So let's practice that with some actual problems here. So here we have to find the horizontal asymptote. And to do that, we actually don't need it factored. We actually want it multiplied out to see what the degree of the top and bottom are. So here I can see the degree of the top is 1, the degree of the bottom is 2, so the degree of the bottom is bigger. That means the top is smaller. So my horizontal asymptote is y equals 0, or the x-axis. Here, the degree of the top and bottom are the same. They're both x squared is the largest exponent. So the line y equals 4 over 2, which equals 2. So my horizontal asymptote is y equals 2. Now, for your x or for your vertical and horizontal asymptotes, it is really important that you write y equals 2, not just 2. It's not just a number. Same thing with the vertical asymptotes. They have to be written x equals and then whatever the number is. Otherwise, I won't mark it correct. It will be wrong because these asymptotes are equations. They are not just a number. They're not just a value. They're an equation. They are a line. And so they need to be written as an equation. All right, now looking at number 6 here, we have a degree 3 over a degree 2. That means the degree of the top is bigger, so there's no horizontal asymptote. Okay, now at the bottom of the page, slant asymptotes. You may or may not have ever heard of slant asymptotes before, but this is another type of asymptote. And basically, this is a very rare thing. The only time you will ever have a slant asymptote is if the degree of the top is 1 more than the degree of the denominator. So exactly 1 more. So if the degree of the top is 3 and the bottom is 2, then you have a slant asymptote. If the degree of the top is 4 and the degree of the bottom is 3, you have a slant asymptote. And the way you can find them is by using division. So I'm going to use synthetic division for this one. We're dividing x squared plus 1 by x minus 1. So in my box, if you go back to our section on synthetic and long division, 1 goes in my box here. And then I have x squared, the coefficient is 1. There's no x term, so I need a placeholder. And then 1 for my constant. I bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 2. 1 plus 2 is 3. This x plus 1 is the equation of your slant asymptote. Okay. It's very rare again that you will see a slant asymptote, but it is possible. So that's what that slant asymptote would be. And we're going to go ahead and end part 1 of our video here, and then we'll resume in the next video with part 2, where we will actually graph some rational functions.